There's a profound beauty in the cosmos, a reassuring order in the way celestial bodies move. Far above, the Earth and Moon have circled each other for billions of years, their dance so reliable we set our calendars by it. This is the two-body problem. One partner leads, the other follows, all governed by gravity's unwavering law. Across the universe, this pattern repeats. Planets orbit stars, binary stars circle each other, all in predictable harmony. Newton's equations let us predict eclipses and plot the paths of comets centuries in advance. This predictability is the foundation of our exploration, allowing us to send probes across the solar system with confidence. The universe, in this view, is a grand clockwork, orderly, measurable, and for a moment, understandable. But this elegant simplicity is only part of the story. It's a special case, a quiet corner of the cosmos. What happens when a third body joins the dance? One might expect a bit more complexity, but the reality is far stranger. The introduction of a third body doesn't just complicate the dance, it shatters it. The gentle waltz becomes a frantic, unpredictable jig. In place of order, we find something far more mysterious: celestial chaos. Picture a simple game of catch between two friends. The ball arcs predictably, easy to follow. This is the two-body problem, Earth and Sun, locked in a reliable orbit. Now add a third person. Suddenly, the game is chaos. Who throws to whom? The ball's path is unpredictable. This is what happens when a third celestial body enters the gravitational dance. The clean lines of a two-body orbit become a tangled, chaotic scribble. In a two-body system, each object pulls on the other in a straightforward way. With three bodies, every object pulls on the other two, creating a constant shifting tug-of-war. The elegant math that solved the two-body dance breaks down. This is the essence of the three-body problem. It's not just difficult, it's mathematically impossible to solve with a single neat formula. There's no simple equation to predict where all three bodies will be far into the future. Instead of a predictable waltz, we have a cosmic mosh pit. One planet might be flung out, another might crash into its star, or they might settle into a new, unstable configuration. The uninvited guest has turned a predictable game into cosmic anarchy. This is why the three-body problem has fascinated and frustrated scientists for centuries. It's a puzzle that resists easy answers. The universe, it turns out, is not always as orderly as it seems. Sometimes just one extra player is enough to tip everything into chaos. In the two-body world, small errors in measurement lead to small errors in prediction. But in a three-body system, the tiniest uncertainty can explode into wildly different outcomes. This is the butterfly effect, sensitivity to initial conditions, the signature of chaos. Imagine predicting the path of a leaf in a swirling wind. Even perfect measurements can't guarantee accuracy for long. Astronomers face the same challenge with three-body systems. A minuscule difference in starting conditions leads to completely different futures. This isn't a failure of our tools, it's a fundamental property of the system. Each body's pull constantly changes the others, amplifying tiny differences with every interaction. Two nearly identical systems can end up with one stable and the other in total disarray. For many systems, the future is fundamentally unknowable in the long term. The universe is not a perfect clockwork, but a place where chance and unpredictability are woven into its fabric. Even the faintest ripple can change everything. Chaos, it seems, is built into the cosmos itself. For centuries after Newton, scientists believed the universe was a solvable puzzle, a grand deterministic machine. That certainty was shattered by Henri Poincaré, who tackled the three-body problem in the late 1800s. Poincaré tried to find a general solution, but the problem resisted every mathematical tool. Instead, he mapped the possible paths of the bodies and found not order but a bewildering tangle. Some orbits were stable, but many were wildly erratic, diverging from nearly identical starting points. This was the first mathematical glimpse of chaos, sensitivity to initial conditions. Poincaré showed that even simple deterministic laws could produce unpredictable outcomes. His work planted the seeds of chaos theory, revealing that the universe is not always a perfect clock, but sometimes a wild, untamable garden. The question of solar system stability was never truly answered. Instead, Poincaré opened the door to a new understanding. Determinism does not guarantee predictability. Despite the chaos of the three-body problem, there are pockets of stability, Lagrange points. These are 5 special spots where the gravitational forces of 2 large bodies and the motion of a third balance perfectly. Imagine 2 heavy balls on a rubber sheet. The Lagrange points are the level spots where a marble can rest. Objects placed at these points can remain in sync with the larger bodies, finding a rare moment of equilibrium. NASA uses these cosmic parking spots for spacecraft like the James Webb Space Telescope at L2 and SOHO at L1. The first 3 points are precarious, like balancing a pencil on its tip, requiring occasional adjustments. But L4 and L5 are truly stable. Objects there naturally drift back if disturbed. Jupiter's Trojan asteroids have occupied its L4 and L5 points for billions of years. Even in chaos, the universe offers islands of calm. These stable points are a testament to the hidden order within cosmic complexity. Humanity has learned to use them, turning chaos into opportunity. The three-body problem isn't just theory. It plays out in real star systems like Alpha Centauri, our nearest neighbour. Alpha Centauri is actually 3 stars. A and B, similar to our Sun, orbit each other in a stable dance. The third, Proxima Centauri, is a faint red dwarf orbiting far from the main pair. For years, astronomers weren't sure if Proxima was truly part of the system. This is a classic three-body problem, 2 stars as one anchor with a distant third body. Any planet in this system feels the tug of all 3 stars, making stable orbits a challenge. Yet we've found at least one planet, Proxima b, orbiting Proxima Centauri in its habitable zone. Its existence proves that planets can survive even in complex triple-star systems. But its long-term fate is uncertain, shaped by the unpredictable gravitational dance. Alpha Centauri reminds us that the universe is filled with intricate, chaotic arrangements. The search for life must account for this beautiful unpredictability. Even in chaos, worlds can endure. The three-body problem's chaos and unpredictability have inspired science fiction for decades. In Cixin Liu's novel The Three-Body Problem, an alien civilization struggles to survive on a planet in a triple-star system. Their world swings between stable and chaotic eras, with civilization rising and falling as their sun's unpredictable orbits wreak havoc. The story uses the three-body problem as a metaphor for existential uncertainty and the search for stability. The Trisolaran's desperate quest for a new home highlights how rare and precious our own solar system's stability is. Beyond this, the problem echoes in tales of starships navigating asteroid fields or rogue planets ejected by chaotic encounters. These stories tap into our anxiety about the unknown and the forces beyond our control. They remind us that, for all our progress, the universe can still surprise us. Stability is rare. Chaos is everywhere. Science fiction turns this cosmic riddle into a powerful narrative force. The three-body problem is more than a mathematical puzzle. It's a shift in how we see the universe. For centuries, science sought ultimate predictability, but chaos showed us that some systems are forever unpredictable. This realization is humbling and vital. Chaos theory, born from the three-body problem, now helps us model weather, animal populations, and even financial markets. It teaches us to respect the limits of prediction and to look for patterns within apparent disorder. The problem also challenges our sense of cosmic security. Our solar system is stable on human timescales, but over millions of years, even it can exhibit chaotic behavior. This knowledge deepens our appreciation for the delicate balance that allows life to flourish. The three-body problem injects mystery and wonder back into science. Not everything can be calculated. Some phenomena will always remain just out of reach. The universe is dynamic, creative, and full of surprises. This riddle is a gateway to appreciating the cosmos for its magnificent complexity. The three-body problem gives us a more authentic, awe-inspiring vision of the universe. Chaos transforms the cosmos from a finished script into an unwritten symphony, unfolding in real time. This unpredictability is not a flaw, but a source of endless creativity. Chaos seeds new stars, scatters planets and ensures the universe is never static. It guarantees there will always be new wonders to discover. We must embrace humility and wonder, accepting that some mysteries will always remain. The joy of science lies in the pursuit, not just the answers. The three-body problem reminds us that discovery is infinite. Next time you look at the night sky, remember the hidden, chaotic dance behind the serene lights. The universe is a grand ballroom, orderly and wild, known and unknowable. It is a magnificent, unfinished symphony, and we're lucky to witness it.